Okay, our next speaker is Ruth Morgan. She's from University College London, and she's going to be speaking to us today about the forensic implications of pollen in domestic dwellings.
Well, thanks very much. I'd also like to thank you all very much for inviting me. The British summer has been a very massive non-event, so to see the sunshine has been wonderful. Thank you. Yeah, I'm from University College London. The department I'm in is called the Jill Dando Institute of Crime Science, which has a pretty unique remit within the UK to change the way people think about crime. That's our mission statement. And we hope to do that by applying good science to both solving problems with the prevention of crime and also detecting it quicker. I do a lot of my work with Dr. Peter Bull from the University of Oxford. He's also here this morning. And today we wanted to share with you some of the work that we've been doing concerning pollen in domestic dwellings. We're in the very lucky position that we're able to do an awful lot of research into questions that are raised by casework. We're not on a timed budget, and we're able to explore some of the questions that arise. An awful lot of the work that we have been doing is in the field of forensic geoscience. A particular area is soils that we're very interested in, and in particular how you can use quartz grain surface texture analysis to be a provenancing tool. But that's an aside. But today it's pollen. It's obviously a type of forensic trace evidence that can have real important implications for casework. So this is where we're going. A brief outline of a brief justification of experimental studies. And then the three examples are the three different experiments that we've been running with our graduate students. The first one deals with spatial and temporal distribution of pollen within a room. It just threw up some very interesting results that really rather surprised us. Secondly, at a smaller scale, spatial and temporal distributions of pollen on paper. Again, that really, it was a hypothetical question that we did the research in answer to, again, some slightly surprising findings, at least to us. And then thirdly, how does pollen survive under extreme heat conditions? Arson, terrorism cases have led to that, but I'll come back to that later. And then finally, wrap up with some implications for forensic geoscience. So I was really glad I was speaking this morning after yesterday's session, because I think this justification for doing experimental studies was very much addressed yesterday with the idea that we need to have an idea of context if we're going to interpret, analyse and present trace evidence accurately and meaningfully. But just a few things. We need to mimic forensic reality accurately as possible when we're doing experimental studies. They've got two main benefits. The first of all, they can establish main bodies of theory at a primary level. And an awful lot of people in this room I know have been involved in establishing that body of theory. The secondary level that we talk about is how we can answer specific questions that are specific to a particular case. And that adds this sort of secondary level of context so that we can interpret trace evidence from a particular case meaningfully. And it can be key for accurate interpretation. So, without further ado, I know we're not much time. It was going to be a whistle-stop tour when I had half an hour, so it will be even quicker. The majority of this work, just before I start, is unpublished. We're writing it up at the moment, but where it has been published, the references are at the bottom of each slide. So this first experiment, we were looking to establish whether there were any particular trends and patterns if you had cut flowers or pot plants within a normal dwelling room. And this was the very first experiment we ran, just a bit of a look-see. You can see there's the diagram of the room there, and that's another aspect of it. We had 23 different sampling points that covered a variety of different surfaces, from the materials on upholstery to carpeting to smooth, hard wooden surfaces. We put flowers in the room. I think you can just about, oh no, hopefully you can see there are two jars of flowers on two tables, different ends of the room. We put them in, we waited for 9 days, sampling every 24 hours at those 23 different sampling points. When they died, we took them out of the room and continued to sample for a further 10 days. And broadly speaking, these are the different pollen types we used. I put this in because they're lovely. I have the best job. I get to look at really pretty things. There's lily at the top on the left, then Lisianthus, freesia at the bottom left, Campanula at the top on the right, Dahlia in the middle, and Hypericum at the bottom. But broadly speaking, we found that there is a significant distance decay. 150 centimetres from the flowers, there was a significant drop-off and a dramatic drop-off after 250 centimetres. We found that the different types of surfaces did have an influence on the amount of pollen retained, but broadly speaking, the distance was a far bigger factor involved. And we also, on a couple of the runs that we did of this experiment, after 40 days, we were still able to collect pollen from some of those sampling points. So the thing that surprised us there was the length of the persistence of the pollen grains within that room. We then decided to do it again in a different room, in a different setting, to see if we could repeat and draw out any more interesting things from the conclusions we'd originally made. So this was the second room that we used. Again, 2 lots of flowers, one by the window on the right-hand side there and one by the window on the left-hand side. We did this 6 times. The first 4 times, it was, again, 9 days with the flowers in the room and 20 days after that. The last 3 runs we did, we kept the flowers in the room for 17 days and then sampled for another 20 days. So the last few runs we were doing 37 days worth of sampling. And broadly speaking, we just used lily and freesia on this occasion. And broadly speaking, we discovered that we were identifying similar trends. So this is a graph of the amount of lily pollen and how much was collected as a function of distance from the source. And the lily behaved in a very similar way across the 6 runs. And we also were able to see that freesia also behaved very similarly to lily. So that was quite nice. It confirmed the distance decay. We were also able to show that in general you get a gradual increase in the amount of pollen present in the room over time. Not necessarily that surprising, but it was good to see that both lily and freesia behaved in the same way across the 6 different runs. And then this one, the 20 days after the flowers had died, as a gradual decrease in the amount of pollen that's present. That's the numbers, the actual numbers that were collected, and that's the percentage as a function of the amount present on the day that the flowers were taken out of the room. And you can see that broadly there's this decline. It looks like a very standard decay curve. After 20 days, around about 30% of the original pollen present, not necessarily that much, but given how much pollen was in the room, 30% is 30%, so it's definitely worth looking for. We're actually extending this study now to a 3rd room. Because of the longevity of the pollen in this instance, we're now looking at the presence of pollen in the room over 6 months. It's a room that's used by a family and pets. There's dogs and cats in the house, and we're looking to see what's going to happen with that longevity of pollen. What are the patterns that sort of seem to emerge over a much longer time frame of 6 months? We're also thinking that will probably have pretty significant implications for, so every contact leaves a trace, but what about the contact of the contact of the contact? Secondary, tertiary transfers going on, and how will that have an impact on the way we interpret evidence? We're hoping to maybe apply some social science theories, network analysis to try and provide a bit more context to the way that evidence behaves. The other finding that we found was that the sampling points that were near external windows and doors on occasion got additional pollen types that obviously we hadn't put in the room in the form of cut flowers. You can see here that there's quite a lot of grass pollen present on a few of the runs, and there's a little bit of oak and a tiny bit of pine. That was consistent with the garden environment at that room outside the house. And obviously, we're in a temperate climate. We've got quite a very, don't we know it, serious seasons going on in the UK. So again, that's just another dimension that we're hoping to look in our extended study to see if that's going to add to the specific assemblages that we can maybe find within internal domestic dwellings. Just a summary of the findings then. Distance decay is a significant one. The persistence of these particles is so much longer than we had thought of, and therefore that's got big implications as to what you might pick up when you make contact with something in that room. The studies that we've done seem to be pretty repeatable. They're producing similar results in a variety of different settings and over different timescales. Disturbed, undisturbed sites, maybe not surprising, but disturbed sites have yielded less pollen over time in comparison to the undisturbed sites, but still the distance decay was a more significant function. Soft v hard furnishings, textiles obviously, well, textiles did retain more pollen, but there was still some present on the hard, soft furnishings, and they seem to transfer more readily than those retained on the textiles. And the outside influences, what's coming in from the outside to enhance or augment that particular specific assemblage. So that was the first study. Second study. Now this was precipitated by the hypothetical question of document analysis. Is it possible that pollen is retained in the ink that's used to write on the paper? And if so, does that mean that we can identify that, say, Granny's will has been dated in August and it's been written, but on analysis we're finding daffodil pollen. Daffodils are only really available in the UK March, April sort of time. Is there a way that we could use pollen to establish temporality and maybe throw light on a question document case? So our premise was that pollen was likely to stick to ink. Could we find it? Could we collect it and analyse it? So the first experiment that we ran, we set up templates and we wrote this letter E in 8 sections of the A4 piece of paper. The template ensured that the E was written in the same place each time. And we looked at 9 different types of ink and 6 different types of paper. The very first experiment we ran, we wrote on the paper. We then simulated pollen rain on that paper. It was then folded, put in an envelope, and posted back to the lab. And we used, on this very first instance, UV powder as a proxy for pollen because we could use UV lights and digital photography to pixelate images and therefore quantify the amount of UV powder or pollen present. And this is what we found when the document was written on before the pollen rain. I hope you can see that there, that broadly speaking, the powder is retained in the creases of the paper rather than on the ink. And that became apparent that it was the paper that was more important as a retainer than ink was. We then changed tack and we looked at pollen that had pollen rain on it first. It was then written on in the same way and then folded and then posted and then analysed. And you can see here that we actually had a slight change in the spatial distribution. Again, it wasn't the ink that was important, the paper was important, but what became apparent was that the patterns were significantly to the right bottom corner of the letter E. You can see there, that's because the hand was leaning on the paper and exerting pressure and therefore creating patterns of the UV powder distribution. We then repeated all those experiments again with pollen. Very similar results were achieved. And yeah, that was lily, tulip, and alströmera pollen. And so broadly speaking, the UV powder did seem to be a reasonable proxy for pollen. It does persist on documents, but much more on the paper than on the ink, which surprised us. The different types of pollen all exhibited the same types of behaviour. The thing that just was quite an interesting aside, the paper was a rich source of pollen, but the nib of the pen and the corners of the envelopes were also very, very important sources of pollen, which might have implications for other small trace materials that could be on documents. Okay, rushing through final experiments. How does pollen behave under extreme heat conditions? This was in response to another, it was casework. My colleague Peter Bull had been in a number of cases where terrorists had used incendiary devices to destroy getaway cars in order to destroy biological, botanical, and geological evidence. The question was, if you do manage to recover some of these types of evidence, are they actually viable, or will they have been corrupted by the extreme heat? So we had some very friendly people in the Cotswolds, the fire brigade, who allowed us to put thermocouples in their exercises for putting out car fires. There's a lot in the literature about this, and broadly speaking, things that are protected during a fire are often pretty well preserved. So this was under the carpet in the trunk of the car. The items that were placed in there all seemed fairly well preserved after the fire. And that's been shown to be the case in domestic dwellings as well. Now, the good thing for us is that it was the car trunk and then the footwells that seem to be the most protected places in these vehicles. The best thing about the car footwell is that's where, as geoscientists, we often find the majority of our material that's of interest, because it's on your shoes, you get in the car, whack it on the pedals as you're driving, it falls off and nicely collects in the bottom. So we were on to a hopeful start. This is the work of Paturi and McElroy, who did a similar thing in domestic dwellings. And I've just put it in there because you can see there that on the floor, which is the green line at the bottom, the temperature is really quite low. And the maximum temperatures achieved are really between 400 and 600 degrees C. This was our car fire, and you can see we've got similar range of temperatures, 400 to 800 perhaps, so it's a bit higher. But you can also see that in the footwell, that green line, that it's very rarely above sort of 700 degrees C. So that just gives you an idea of the context. We couldn't do burn too many cars, so we resorted to the laboratory to simulate the extreme heat conditions. And we had 3 different types of pollen, tulip, lily, and daffodil. And we derived a classification system. We basically exposed them to different increments of heat over different time periods. So this is the grains with nothing having happened to them. You can see they're very pretty distinct shapes. This is the same types of pollen, but when they were on the cusp of being distorted. So they have been, you can tell that they've been slightly modified. The shapes are slightly less distinct. The surface textures are slightly less pristine, but they're still identifiable as those particular pollen grains. And then the third classification was where they had been destroyed to the point where you couldn't reliably identify them as a particular type of grain. The lily was particularly in the middle there, quite spectacular. It just seemed to sort of melt and decompose into a mess, basically. Now, this is interesting because whilst we discovered that if you expose the grains for between 5 and 10 minutes, that broadly speaking, they would be surviving intact at about 500 to 520 degrees C, and over 15 minutes, so between 15 minutes and an hour exposure time, it would reduce to about 420 degrees C. So that was a lot longer than we thought and a lot higher than we thought. Over 24 hours, if you exposed the grains, they would be intact. For tulip, it was 50 degrees C. For daffodil pollen, it was 100 degrees C. And for lily pollen, it was 200 degrees C. So they exhibit some serious longevity. And for all 3 of the pollen types, it was possible to identify them after 30 minutes at 400 degrees C. So there's an awful lot of numbers. I haven't included them here. But broadly speaking, the temperature was higher than we expected and the time frame was longer than we expected. And that just shows you that the slight variations between the 3 different pollen types. But broadly speaking, they were surviving intact at those sorts of temperatures, sort of between 450 and 520 for 5 minutes, and only really reducing to about 400 degrees C at 30 minutes. So there's a variability in the way pollen persists, but it's a much higher threshold than we might have imagined, and they can withstand these higher temperatures for a lot longer than perhaps we might have imagined. So therefore, it's worth trying to collect it. If it's been in a fire, it's worth trying to collect it, and it will be obvious if it's viable or not under an electron microscope. So I hope I've been able to share with you some of the findings we've had. We've had a lot of fun doing it. Pollen is very important. That's been well established in the literature. But hopefully these studies are just providing that extra level of context within which we can interpret it a little bit better. There are very significant spatial and temporal trends at a variety of scales, and also those assemblages that will be present will be impacted depending on the conditions that you're looking at. And these distinctive combinations obviously do have a very significant potential to aid investigations, mainly because if we can understand the context, we'll be able to interpret their existence better and therefore present the evidence better. So I hope I haven't bored you too much with showing some very obvious things, but a wise man once said to me that to say that is obvious is easy, but to state the obvious in the first place is infinitely more difficult. So thanks very much for your time.
Are there any quick questions for Ruth?
I have a comment, real quickly. I don't know if you're aware in your research is Max Freiselzer, one of my boyhood heroes, actually solved a case dating a document after the Second World War. He examined, as he was examining the ink lines under a microscope, he noticed a little bump in the ink, and recall in those days they used, especially in Europe, he's from Switzerland, was from Switzerland, they used fountain pens. And when he extracted the little bump in the ink, it was cedrus pollen, and the document was actually known to have been signed by an open window in a hotel outside which there was the proper tree. So he preceded your work by a little bit there, but actually found it a very great use. It's published for anybody who's interested and who reads German also. It's in Herbert Stracke's Spore- und Pollenkunde. There's some examples in there, and that's one of them.
Thank you.
How did you collect your samples?
It varied. Which experiment were you particularly?
The first one.
The first one. We used taping, and we taped a specific area a set number of times in each location, and then counted pollen grains on those stubs.
Along those lines, how did you, so you marked off where you expected to find on the taping the pollen grains? And how did you remove them and observe and look at them?
Right, so we put the tape on an SEM stub and then used that stub to collect it, so it was all on one stub, so we didn't have to treat it afterwards.
Thank you, Ruth.
Thank you.